Good morning, everyone. Welcome to meggerea webinar. I'm Grace, Megger Hong Kong. Today, our topic is a new and superior way to trace ground faults, presented by our product manager of battery testing products, Mr. Andrew Sagl. This is a live webinar. You're automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of your screen. We will answer your question in the Q&A session. At the end of the webinar, please help us fill in the survey, which is on the right-hand side of your screen. We'll be sending the presentation materials to those who completed the survey. Attendees will be able to download an attendance certificate after they have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time after the webinar. So without further delay, let's start now. Thank you for joining us today. Andy, I will pass the time to you now. Thank you.
Thank you very much, and good morning, everyone. Today we're going to be discussing ground fault locating. And this is the agenda we're going to be following. We're going to be first examining ground faults and their dangers. We'll cover the common causes of them, how to trace the ground faults, and the pitfalls we can encounter during tracing, how to overcome the pitfalls, and then we're going to actually cover some actual cases that we had. So first, ground faults and their dangers, okay? Very basically, what is a ground fault? A ground fault, very simply put, is an unwanted path to Earth. And it can be due to many different things: damaged wiring, faulty insulation, dust, dirt. And now, one thing to understand is that when we speak about these ground faults, these are on ungrounded systems. Now, when I say an ungrounded system, I don't necessarily mean it doesn't have a ground. It means it has a high impedance ground. And why do systems have this? What is the benefit of this? Well, these types of grounds or ungrounded systems are used where you have critical systems that can't trip offline. If you have a grounded system, then when you get a ground fault, what happens? A breaker trips and equipment goes offline. So in ungrounded systems, if you get one single ground fault, you will not go offline. Now, here's where the problem inherently lies. If you get a second ground fault on the same circuit, now that can lead to high levels of current flow and can lead to catastrophic failures. So for these reasons, when you have these ungrounded systems, you're going to have ground fault monitors on them. And those ground fault monitors are going to indicate when you have a ground fault. And they'll tell the operator that there is a ground fault, but it will not tell them where the fault is located. We have to trace that. And the obvious dangers of ground faults are they can be hazardous to people and equipment. Think about it. If you have a very low resistance ground fault, that has the potential to draw high current. That can create heat. High impedance ground faults can create high differences of potential, can be shock hazards. So some of the issues you can run into is overheating, fires, shock, personnel being shocked. And in some areas like North America, there's actually government guidelines that they have to locate ground faults. They must be located, or the utility can be fined. So what are some of the common causes? Well, some of the very common causes, one is pinched wires. This can be due to maintenance. I've seen this multiple times. Maintenance crews come in, they do their work, and in the process, they pinch something and create a ground fault. Damaged wires, pests, we see this all the time. When you have equipment that's outdoors, pests can get in there and they will damage the wiring. They'll damage the insulation and create ground faults. Faulty insulation. I mean, really, that's what our ground faults are. They're insulation issues. And a lot of these, especially when you get into your high impedance ground faults, are due to water ingress. We know that when cables lie in water, their insulation over time breaks down. As that breaks down, that water seeps in and creates a path to Earth. So this will create a high impedance ground. And we see quite a few of these now. They're mostly due to moisture, and as these severe weather events keep occurring that we're seeing, we expect these to become even more common. Some other causes we see are obviously faulty equipment, dirt, electrolyte leaks, even spider webs and insect nests. So when I say faulty equipment, what's happening inside the equipment is something is breaking, some insulation is getting damaged, creating a short to the chassis. Now the chassis is always tied to earth. Why is it tied to earth? Because it's a safety. If the chassis is tied to earth, it doesn't become hot, so you don't get shocked by it. Okay, but when you have a failure inside a chassis, that creates a ground fault. Dirt or corrosion can cause faults to earth on connections. We just found one of these yesterday on a system. They traced out a ground fault, and it was actually a lug that had corroded, and it corroded over to earth and created a ground fault. That's another common cause. Electrolytes. When you're dealing with battery strings, you get a cracked jar, and electrolyte leaks. Remember, electrolyte's conductive. It can create a path to earth. And this is another instance one. Spider webs, insect nests, people do not think of these things. We had one intermittent fault that occurred every time it rained, or actually even early in the morning, because there was a spider web. Water condensed on the spider web and created a path to earth. And that was actually the cause of the ground fault. So there can be many different reasons that ground faults occur. So how do we trace a ground fault? What's the proper methodology to use? Well, as I said before, now recall, when we're on an ungrounded system, we're going to have a ground fault monitor on that system. Now, for a ground fault monitor to work, it has to be tied to earth itself. So it has a path to earth. That path to earth of the ground fault monitor is going to be in parallel with the unwanted ground fault that you have. Okay? So it will create a parallel path. Now, if you have a low impedance ground fault, the ground fault's very close to earth, it probably won't be an issue because the majority of the current, or that you're going to use to trace the fault, will flow through the ground fault. However, if you have a high impedance ground fault, then you can run into a scenario where the majority of the tracing current you're going to use to trace the ground fault will flow through the ground on the ground fault monitor and not through the ground fault. This is why best practice, before you even start tracing a ground fault, it is recommended to remove the ground from the ground fault monitor if possible. This is not always possible to do, and there's different ways to do it. Some methods require removing a wire. Other methods where you have the ground fault monitor built into something like a charger, a lot of times they will have breakers that you can throw that will open the earth connection on the ground fault monitor. But there are scenarios where you may not be able to isolate the ground fault monitor, and that's actually one of the case studies that we're going to look at. So what are the basics of ground fault monitoring? Really, the whole basic concept of ground fault tracing, rather, I should say, is quite simple. You have a ground fault to earth. So what we're going to do is we're going to take a transmitter, we're going to connect it between the side of the circuit that has the ground fault and earth. We'll then put a difference of potential between them, which will push a current through the ground fault. Then we use a separate receiver with a current clamp on it to trace the path of the current to locate the ground fault. It's a very simple concept. However, nothing is as easy as it seems. There's many different pitfalls you can run into during ground fault tracing. And some of these problems can include high leakage capacitance in the circuit noise. High impedance faults create their own challenges. And there's always the hazard of tripping a breaker. And there's also the possibility of magnetizing a current clamp during the ground fault tracing. So let's talk about stray capacitance for a little bit here. So all cables have capacitance. I mean, if you think about it, let's think about what a capacitor really is. A capacitor is two conductors separated by an insulator. Okay, what's a wire? A wire is also two conductors separated by an insulator. So they are going to act like a capacitor. They'll have a large amount of capacitance in them. Now remember, we're tracing on a DC system. So we're going to be inputting either a DC pulse or you're going to be inputting an AC signal. Now, to DC, once the capacitance charges up, it no longer presents a path. However, to a pulse or to AC, capacitance represents a path for the current flow. So if we don't take that into consideration during the ground fault tracing, you could end up tracing stray capacitance all day long and never find the fault. Noise is another common problem we run into, especially in today's world where we're seeing a lot of SCADA systems, a lot more digital noise on there. This can interfere with your tracing signal, and it can make locating the fault extremely difficult, if not impossible. So this is another thing we need to actually take into consideration when tracing a ground fault. And another thing we're going to look at is high impedance faults. Cables in water, that leads to insulation breakdown. And, basically, to be honest, if you have a low impedance fault, if your fault is 50 ohms or lower, it's really going to be relatively easy to find, because the majority of the current that you're going to trace with will flow to the fault. When you get these higher impedance faults, which can be over 100K, these present more of a challenge to locate, because you have to be able to generate enough current to locate the fault and overcome both your signal to noise ratio from your noise in the system and the stray capacitance. And you also have to be careful not to apply too much current, because you could dry the fault out before you even find it, assuming it's due to water ingress, which is one of the most common causes of high impedance faults. And this is the thing we really don't want to do here, and be very careful not to trip a breaker. If a breaker is tripped, then critical systems have gone offline, and this is exactly what we do not want to happen. Now, this can occur when a breaker is close to already tripping and the operator applies too much current trying to trace the fault, and or misuses the system. That's another way you can actually trip a breaker. So we're going to discuss a little later on in this presentation how to avoid that. And this is another issue that we've run into. Now, if anyone has done ground fault tracing, on a DC line, usually you go to work on de-energized lines. However, that's not always the case. You can run into scenarios where you're on live DC. If you place an AC current clamp on a energized DC line, what happens? Well, the core is going to saturate, and the clamp is going to magnetize. Once that happens, that means you can't open it anymore. It just got stuck on the line. The only way to get it off is to either de-energize the line, or I've seen this happen too. They break the current clamp to get it off. Now, as I said, most lines are de-energized. However, that's not always the case. We've had multiple cases where people have put current clamp, AC current clamps, onto energized lines, and they've ended up having to break the current clamp to get it off. So how do we overcome all these different pitfalls? Well, when we're talking about stray capacitance, one of the things that is a very traditional method to try to deal with this is attempting to tune out the capacitance. And typically this would be done with an internal Wheatstone bridge. And the Wheatstone bridge, the way that would work is you would basically be placing a capacitance 180 degrees out of phase with what you're measuring, and attempting to adjust it until you can minimize your measurements. And it does work, but it is a time-consuming methodology. Now, keep in mind, I mean, when you're tracing, you're going to get on a line, you're going to see current. So let's say my total injection current into my ground fault is 5 milliamps. I go to the panel and I see 3 lines drawing current. One is drawing 2 milliamps, the other's drawing 2 milliamps, and the third's drawing 1 milliamp. Which one has the fault? Well, the problem is you may find out that 2 of them are just drawing current because of high leakage capacitance. And this is why we need to figure out which one is the real fault. Now, when working with ground fault systems, ground fault tracers, there is 2 different technologies that will be used. Some will apply an AC signal as a tracing current. Others will supply a DC pulse. Now, attempting to tune out stray capacitance with a Wheatstone bridge type technology, it will work, but it can be cumbersome and really can take some skill to do. And when dealing with high capacitance circuits with a pulse technology, that actually provides more challenges. So let me ask this. What happens when I apply a DC pulse to a capacitive circuit? What's going to happen is you're going to start getting a charging effect. And the circuit will charge up and you'll see a ramp on the DC pulse. The higher the capacitance in the circuit, the more reduced the pulse becomes. So it can be very difficult to try to locate the pulse on a capacitive circuit. So when you have high capacitance throughout your whole circuit, a pulse can get dampened out and be extremely difficult to locate. When you're dealing with AC, what happens when you apply AC to a capacitive circuit? What's going to happen is you're going to get a phase shift between the voltage and the current. The magnitude is not really affected, but the phase shift allows us to measure a phase angle. And from that phase angle, we can actually calculate the real fault current and the reactive current, or the reactive current being the current going to stray leakage capacitance. So if we go back to the example that I gave a little while ago, where I said we had a total of 5 milliamps coming out of the transmitter, that's our fault current. We go to the panel, we have 3 lines drawing the fault current, 2 milliamps on one, 2 milliamps on another, and 1 milliamp on the third, which is the right one to go with. With this type of technology, You can measure all three, and you'll see which one actually has the real fault current and which ones are just drawing stray leakage capacitance, or just drawing current due to stray leakage capacitance. There's no tuning out required, and there's no type of syncing required. You literally just take the measurement, and you can see that. And that is very unique in trying to locate these type of ground faults on energized systems. So the benefit of this is you're not going to be tracing the wrong path again. And I can tell you, anyone that's ever done ground fault tracing and started tracing a capacitive line, you can be tracing all day. This will save quite a bit of time. So now let's move on to noise. How do you overcome noise on these systems? Because what the noise can do is it can cause your reading not to stabilize. You'll put the current clamp on the line, look at the receiver, and the current measurement you're looking at just never stabilizes. It keeps going up and down and up and down, and this is a telltale sign of noise on the system. Okay, so when we have a DC system, when you have noise on that system, that current from the noise is going to flow through the system and come back on the return line. But remember how we hook up the transmitter. The transmitter is not connected between the circuit and return. It's connected between circuit and earth. So the transmitter current, although it goes through the circuit, returns on earth, not on the return line. Okay. So they return on different paths. So there's two ways you can do this to cancel out the noise. One, if your return line is near the line you're measuring, you can just simply put the current clamp around both the return line and the line you're measuring. What will that do? Well, that will cancel out all the noise on the system and only leave the transmitter current, which is coming back on the earth line. So your measurement will stabilize, and you will literally have canceled out all the noise on the system. Now, however, when you're at a panel, typically the lines are pretty close together, and this isn't difficult to do. Further down the system, this could be more tricky because you may not have a return line close to the line you're trying to measure. In these cases, you can actually use two current clamps. One current clamp put across the line you're measuring and another on the return. What this does is it takes the noise, and again, it cancels it out because the noise will be 180 degrees out of phase with each other. But that will cancel out, but the transmitter signal will stay constant. So one of the things we have done is we have stackable jacks, so you can use two current clamps on the system in areas where you do have a lot of noise. Now, like I said, if you're at a panel, typically one current clamp, you can put it around both lines and you'll cancel out everything, all the system noise. But further down in the system when you're tracing, that could be more challenging. Hence, why you can just take one current clamp, put it around the return line, and then do your tracing and have the noise in the system canceled out, and you get a nice stable signal. Okay. And that's everything I just said there. Okay. And the one thing you always want to do when you're doing this method is make sure that the arrows of the CTs are in the same direction. Okay, because they have arrows pointing toward the loads typically. Okay. Now, as I said before, with faults, you can get high impedance faults on these systems. Now, a low impedance fault, 50 ohms less, that's going to be relatively simple to trace. But a high impedance fault, when you start getting up into the hundreds of K, then what happens is that you're going to be tracing with very minimal energy. So you could have a fault that's drawing, microamps, and you could have stray capacitance that's drawing magnitudes higher than that. So when you try to trace the signal, it's going to be very difficult to identify which circuit has the real fault. So there are several options here. One, you can increase the voltage on the transmitter. You increase the difference potential across the fault and the transmitter. You increase the current flow. Some instruments on the market will allow you to increase the voltage up to 1,000 volts. That actually is a hazard, and it can trip breakers. And it's a hazard to the user. It's a shock hazard. In addition, when you increase the current, you're increasing the heating effects. Remember, IR power is IR squared. So you're more likely to dry out the fault before you locate it. So you're better off trying to locate this with minimal energy. This is again where you get a benefit by being able to measure the actual current drawn by the fault versus the current drawn by stray capacitance. So even in this example here, you can see how low the current is going to the fault. Its magnitude's lower than what's going to the stray capacitance. If you were just to trace the largest current that you see, you'll never find your fault. This way, you know whatever line you go on, where you're actually locating, where you get the fault current, and trace the proper line. This allows you to locate high impedance faults without the need for increased current, minimizing the chance of drying out the fault. Now, obviously, if the reading does go away during your tracing, the fault could be extremely far away. And if it does dry out, once that dries out, you're not going to find it. So the thing to do at that point is mark where you left off, because the next time it rains, that's where you can pick up again, because that's where the fault is. But tracing with minimal current is the way to look for high impedance faults to make sure you do not dry them out. Tripping breakers. And again, breakers will trip if too much current is applied. This we've seen happen when people turn up the voltage and then turn on the output. And this can create a situation where the breaker will trip, because think about this. If you turn up your voltage real high and then turn the output on, what are you basically doing? You're creating a transient. That transient is going to go right through, and that is what can trip your breakers. So one of the things we've learned and we have incorporated in the system is a twofold approach to this. One is that on this unit, you can actually set the current limits and voltage limits, and they are password protected. This means that you cannot accidentally apply too much current or too much voltage. This way, engineers can examine the system, and in these systems, they may want to limit the amount of current or the amount of voltage, or both, that you can put into the system. And again, this is password protected so that it cannot accidentally be overlooked in the field during use. The other thing we've done here is, in order to actually inject current into the system, the outputs have to be turned on first. So you cannot, there's no way to actually up the voltage or put a difference potential across the path and then turn on the output. So this always creates a nice, smooth, slow ramp up. So there is no chance of getting a transient pulse. So the odds of being able to trip a breaker have been completely minimized on this system. Now, this is a really interesting one. How do you deal with this? When you place a CT on an energized line and the core saturates and gets magnetized. I mean, when you put a CT on a line, you're really not going to know at first if that line is energized. And we want to use a CT that has a good core in it because, I mean, one of the obvious things people will say is, well, why don't you use a Hall effect? Okay, that will not magnetize. However, a Hall effect is not going to be sensitive enough to measure the low currents you're looking at. You actually need to have a core. This is why you don't see Rogowski coils used or flexible CTs in these applications, because they have air cores in them. And they have very low permeability, so they're not very good at trying to capture these very low frequency, very low magnitude signals. Typically, you need something that has a high permeability, so you need something with a good core. So you can pick up the small signals, but the downside of that is that they can magnetize on DC lines. So how do you deal with that? Well, what we do is we have a customized CT that has a mu metal core, and this is basically a nickel alloy core, and it will not magnetize like an iron core will. So even if you put this on an energized line, it will not get stuck. And we have even smaller clamps that work with flux gate technology that also will not magnetize on energized lines, so it eliminates that potential issue. So now what I'd like to do is just go over a few actual cases. And these cases are going to be some of these pitfalls that we have seen in the field. So this is one of the distribution substation in Chicago. They were using this system here, and they were searching for a ground fault that they had for over 2 years that they could not locate. We went in and we found it in under 2 hours with this unit. And the main issue they were having was that the panel was in a different room than the battery string. It was actually quite a distance away. So they had a very, very large panel that had virtually probably over 100 circuits in it. And each circuit was drawing current, a small amount of current. So there was no way for them to really determine which circuit had the real fault. So, okay, so on this particular system, they were only getting one current, the total current. So again, it's very hard to determine which one has the real fault, and they would have to try to tune out each circuit. And it was such low values, it just was not working. You could not locate it. And it wasn't possible, especially since they were in different rooms. Made it very difficult. Now, we've actually, to deal with this type of situation, we have developed a patented capacitive pickup clamp. And this actually attaches to the receiver along with the current clamp. With this, we basically placed it on one of the lines in the panel. Now, if you think about it, when you have voltage applied across the circuit and earth, that difference of potential is going to be through every line. But the current will only flow through the lines that have either leakage capacitance or the real fault. So it's not like we have to move this around. We just basically place it on one line, because all we're looking for is basically the zero crossing. So we placed that on one of the lines, and then we were able to take the current clamp and go through each individual circuit, and we literally could see this one's all capacitive, all capacitive, all capacitive. Then we finally found a line that actually had the real resistive current. So out of the 100 circuits, there was only one that was actually drawing real resistive current, and we found it right away. Okay. So again, we just saw it right on the top display, and in fact, the unit alarmed when it was on that circuit. So it actually alarmed and said this is the circuit that has the real fault. It was very simple to identify. So we had a visual and audible tone that came out. And then, now this substation was about 5 stories tall. And for some reason, the battery string was on the top floor. And they didn't have any elevators, which was just, I can't imagine how they even got the string up there to begin with. So the one benefit of this unit too is it's light, so it's very easy to carry up there. But the fault was actually in the basement of the unit. And so the transmitter was left on the battery string, and we just moved the receiver, took that with us, and literally traced the fault into the basement. And it was on, we actually found it on a pump that was down there. So that was a huge thing to be able to locate that fault after they had been looking for it for 2 years and find it so quickly. Now, this is another case study. This is another substation that is located in, I believe this one was in Tennessee, I believe, or Alabama. I'm not sure, one of the two. But they were actually tracing the fault that they had, and they traced it to the battery charger. And they used multiple instruments to confirm it was the battery charger. So they then replaced the battery charger, and the fault was still there. So now they had no idea what was happening. So we connected up to the battery string, and immediately one of the things we saw was that they had a negative fault to earth. We were able to verify that. However, when the current was applied, we noticed the measurement on the transmitter was a little bit unstable, which is very odd to see. So we had turned off the transmitter, and the receiver that we have has a mode that allows you, now the transmitter outputs a low frequency, just above 5 hertz. So the receiver has a low pass filter in it, which only looks at very low frequencies. But due to problems like this, we have a mode in it that allows you to take that out and measure line frequency, 50 and 60 hertz. And sure enough, as soon as we looked at that, we found they had AC coupled onto their DC system. So we traced the AC that was coupled over it right back to the chargers. And there was a wiring problem in their chargers. That had to be corrected, and we actually isolated that. And then we were able to very easily locate the fault to a relay that was in the system. So by having the ability to do that troubleshooting, we were able to very easily isolate that fault. And this was a very interesting one here at another utility. They had the situation that I had mentioned earlier before, is that they had a ground fault monitor. They could not isolate the ground on it. So, and they had a high impedance fault. So when the tracing current was applied, the majority of the tracing current went through the ground fault monitor. So there was very little current flowing through the actual ground itself. So they had many lines, and every line had a little bit of leakage capacitance on it. So what does that mean? Well, the majority of the current's going through the ground fault monitor, and every line you go to measure has just a tiny bit of current on it. So how do you distinguish the circuit with the ground fault? And again, this is where this method basically saved the day for us, because we were able to isolate and locate the line that had the very low current on it, the real active current that was going to the fault. So we could distinguish the current that was going just to leakage capacitance and the current going to the fault. And we could do that without disconnecting the ground fault monitor in this case. I mean, it's easier if you can disconnect it, but if you can't, this method allows you to actually still be able to locate the fault. Okay, so it was really quite simple, because when we measured the circuit with the fault, we saw it, and as soon as you just went to any other circuit that just had leakage, there was no value there on the real active current. So it's a very easy way to do this. So with that, I am going to open up the floor to questions.
All right. Thank you, Andy, for your wonderful presentation. So you now come to the Q&A session. If you have any questions, you may type in the question box. And for those of you who are leaving, please remember to help us fill in the survey, which is on the right of your screen. We'll be sending the presentation materials to those submitted the survey. And also, you can download an attendance certificate at the bottom control panel, which is the icon on the right-hand side. All right, I think we have the first question here. Andy?
Okay.
Yes, it is quite a long one. I'll read it out. Some equipments are designed to have high inherent leakage current, which is normal operations, will seem to be like a ground fault and trip the ground fault relays if the settings are not set above the threshold value. Is this type of equipment recommended safe to use? An example is the lift motor, and also does this inherent leakage determine detrimental during normal usage?
Okay, well, whenever a breaker is tripping, the first thing you have to realize is the breaker tripping due to voltage or current. That's a design issue. Some can be set up to trip for voltage, others for current. So even if it's negative or positive, it's really going to depend on what limit you're surpassing there. So before using anything on that system, it's best to consult with the design engineer and have the recommended maximum current values or voltage values defined. Then you can program them into the transmitter. So yes, this is safe to use on that, but I would recommend that you find out from the engineer what the maximum limits are. This is one of the things that is done in many of the nuclear sites here, is that before they use anything, they have to program in the maximum limits they can put in.
Okay. And the second question here is, how about detecting ground faults in motor of 500 volts? Could we detect the ground faults in online conditions?
Okay, that's going to depend on whether it's a grounded system or an ungrounded system. So if you have a system it's a grounded system that has a low path to earth, this is not the type of system to use for that. If you're having an ungrounded system, that's possible. Now, also, this could also be used on an IT grounded AC system. To do that, you would need a special filter, which is optional. But let me first describe what I mean by an IT grounded AC system. When most AC systems use what's called a TT ground, and that would stand for basically the first letter in that scheme is the ground at the source, the second letter is the ground at the load. So a TT grounded system, which is the most common, is a Terra ground. It has a rod at the source and a rod driven into the earth at the load. In these type of systems, when you get a ground fault, a breaker trips. An IT grounded AC system is isolated at the source and tera at the load, so it has a stake at the load. In these type of systems, these are used on critical applications, and they will not trip a breaker with a fault. But you do need to locate that fault, and that can be done as well. But as far as the motors go, if they're on a ungrounded system or a high impedance ground, yes, you can actually find them. In fact, one of the issues you can have with motors is that because of all the wiring in them, they actually present a large capacitive value. So you'll see that a lot of the capacitance will go there. We've seen that in some of our tracing that was done. We had an issue in Switzerland where they had the fault, and we saw it on 3 lines. 2 of the lines were just capacitance due to these big motor loads that were on there, and the fault was actually on the other line. So the ability to differentiate those really paid off. So in answer to your question, yes, it can be used on that, provided that you are on an ungrounded or basically high impedance grounded system.
Right, and the next question is, in some installations, monitoring instruments grounding is having a common grounding with the power grounding mesh. In case of intermittent ground faults, how could your Megger ground fault locator help?
Okay, I'm just trying to think about that, trying to visualize that one. So you have a ground fault monitor. That ground fault monitor should be tied to earth. If you have other circuits that are tied to earth, if you have other grounds, if your main return ground is also tied to earth, that's not an ungrounded system. But if it is an ungrounded system, then again, the biggest problem you'll have is that if you cannot disconnect that ground fault monitor, and pretty much any standard you look at is going to recommend disconnecting it. If you can't do that, that can make the tracing more difficult. That's why in those particular cases, what you need to do is when you apply the current from the transmitter, what you would do is take the current clamp and you would put it around the output of the transmitter. This way you can see the total current going to the fault, and you'll see the total reactive current drawn by stray leakage. So now you have these 2 values. So you may look and see that the total value going to the fault is, for example, maybe it's 10 milliamps. Well, now if you go and look at the ground on your ground fault monitor, you could see that that might be about 8 milliamps going through that, and only 2 going to the fault. So now you sort of know the value you're looking for. So when you go through the panel, now you realize I'm only looking for about 2 milliamps in there. And again, you're going to see the real current. You're only interested in that. You're not interested in the straight leakage capacitance current or the reactive current. So although it's easier to disconnect the ground fault monitor, it's not required in the system because you can, but you have to know to measure the total out of the transmitter and then measure what's on that earth on the ground fault monitor. So you can see what's going there, and then you can see what the difference is and know that's the value you're looking for.
All right, I guess we don't have any further questions. If you have any more questions, you can send us email to meggerhongkong@megger.com. You can also go to our website, megger.com/webinars for official webinars. And on next Wednesday afternoon, we're having another webinar on paradigm shift in high voltage circuit breaker testing. So if you are available, we will encourage you to join this webinar as well on next Wednesday afternoon time. So please help us fill in the survey before you leave, and also don't forget to download the certificate. Thank you, Andy, again for your time and presentation. Thank you all as well, and we hope to see you again next time. Thank you, everyone.
Thank you.
Thank you, everyone.
Thank you.
Bye.
Thank you, Smitty and Bernardo. Michael, bye-bye.